Sure.
So admit all.
So I think the recording has started, but
we can just deactivate the waiting room, and I think everyone will be able to come in.
I don't know how to do that. Oh yeah, okay. So I disable the waiting room. Okay.
Yeah, that should be good.
Okay. Excellent.
Okay. There's people there. Yes. Okay, excellent. So hi everyone. Guess we'll wait a few more seconds for people to join, and then we'll start. Okay, so hi everyone. Today with us we have Cristián Escauriaza from the Universidad Catolica de Chile. Super excited to see what Cristián has to present today. It's a little bit finer scale than maybe what we're used to, but I think it's going to be really interesting. And yeah, Nick, just a little extra is that next week I think we have a break, but we'll be back the week after with our next Landscape Lives talk. Okay, so I think that's everything. I will have the chat will be open towards the end of Cristián's talk, and then everyone's free to ask questions. We can unmute you if you want to ask a question in person. And yeah, I think that's everything. So go ahead, Cristián.
Thank you, Rebecca, and thank you to all the Landscapes Live team for inviting me. I really think that the seminars have helped to maintain the community together, and I was telling the guys that according to the inspiring principles of Landscapes Live, I decided to talk about something totally new. Actually, this is the first presentation I give on this topic, and I'm working on it. So this is all ongoing work, and I'll show you some preliminary results, and I hope you can also ask some questions because it's important for me at this stage of this research. In the research that we do in my group, we work not only in numerical simulations, mostly LES of problems in rivers and the coast. I'm also the PI of the first Marine Energy Center in Chile from the academic side. We're studying tidal and wave energy. I also have a project that has brought me a lot of joy with artists. We are trying to combine art and engineering and working with visual artists to develop something new for our campus, I hope. But the whole discussion has been a lot of fun. And what I'm going to work today about is the work that I've carried out with Professor Megan Williams from Universidad Santa Maria in Valparaiso. We're both part of SIGIDEN, which is a natural hazard center that's been around for about 9 years. And we're, as part of our research line, we're trying to predict consequences of extreme events and try to contribute to disaster recovery, strengthening communities, and address the adaptation challenges to climate change. So today, I'm going to talk about antidunes. Antidunes typically are bedforms that typically emerge in steep slope, mostly in supercritical flow, and they're defined, or they are identified as the sedimentary patterns that are in phase with the water surface, unlike ripples and dunes. And a particular characteristic of antidunes is that they can move upstream. Erosion, even though the flow and bedload transport goes, from upstream to downstream, the erosion is mainly produced on the lee side of the bedform, and they can move upstream in some situations. And they're super interesting from the point of view that we are working on. They're frequently found on sand and gravel bed rivers, especially in high velocity supercritical flow, and they play a significant role in tidal inlets, especially in this bar-built estuaries. They sometimes close. They are formed when the bar opens. They break from upstream when the discharge increases, and they produce this breaching that generates antidunes, and that contributes not only to the morphodynamics of the coast, but also has important consequences on water quality, salinity, change on the salinity conditions, and other characteristics. Also, a scour around hydraulic infrastructures in flash floods, especially, for instance, in Chile, when we have supercritical flows, the bridge piers or other infrastructures exposed to live bed conditions with antidunes, which also can play a fundamental role. And also these regular trains of antidunes structures appear in stratigraphic records, and they can be used to reconstruct old floods. That's the importance of these bedforms in particular. And here you see, this is the Pescadero estuary in California. This is Megan's work, and you see from this picture when the bar of the estuary breaks, you see these antidunes forming. So they actually can control the discharge that goes from one side to the other. We also have seen it, and here, this is a case that is very interesting. We did some sort of analysis after this big flood. This is a flood that we had in the Atacama Desert in northern Chile. Everything that you see here is not sand. We've had to deal with this problems of legacy mining. These are tailings, high in heavy metals that were deposited there 80 years ago or something like that. And we had a big flood in 2015. And actually these conditions that were produced increase the consequences of the flood. You can see here how it looked after this was a very fast flow, 8 meters per second. We were able to estimate after the flood conditions how this tailing bar broke in multiple parts, also in supercritical conditions and with the formation of antidunes probably. You see, and these are the examples of supercritical conditions and hydraulic infrastructure. So in this situation, what we want to do is to try to see if we can simulate these conditions with the objective of first understanding the dynamics of antidunes. Most of the simulations previously have been carried out in ripples and dunes. So we want to try to understand the controlling mechanisms and their evolution and development. Try to see if we can capture the living length and time scales of these bedforms, of the bedform dynamics, and also think about what we need to model them, what is required to model bedforms or this type of conditions, morphodynamics in general. That's an ongoing discussion also that I think it's very interesting. And regarding that first, when you want to simulate bedforms, I think it's important to think that the models need to capture the most important mechanisms that interact with the bed and the sediment transport. And another problem that is typically encountered is the way we have to predict bedload transport in particular in this case is based on formulas that in general have been developed for other conditions, typically for equilibrium conditions at larger scales. And we have to find a way of using them on these higher resolution situations, right? Regarding the modeling of the flow in particular, when turbulence is the leading mechanism, you need to be able to simulate turbulence, right? And in our previous, this was part of my PhD thesis a long time ago. In this case, we were investigating investigating the dynamics of this horseshoe vortex that develops when a turbulent boundary layer encounters an obstacle. Any obstacle, in this case, was a cylinder. But we use here a hybrid turbulence model that combines RANS and LES to be coupled with the Exner equation, and this dynamics of the horseshoe vortex was able to trigger the formation of ripples that had been seen in the experiment in this case. This was later extended by Ali and Fotis, and they developed a LES with near wall resolution in which they were able to actually see all the process of the formation of ripples in a more general experiment in which you had to resolve a significant part of the coherent structures of the turbulent boundary layer to form these crosshatch patterns that later develop in these structures. So in this case, having a good description of the turbulent coherent structures in the flow was important. In the case of Antidunes, on the other hand, and this goes from the work of actually, I think it was his PhD thesis of John F. Kennedy, the hydraulics professor, is typically, and this is work of Francisco Núñez and Juan Pedro Martín Vide that have developed different expressions to predict the propagation, for instance, of antidunes. And most of the cases, due to the synchronization between the bed and the water, is the Froude number relevant. So when we started thinking about developing a numerical model of antidunes, you have to think about combining these three components, which is a very difficult task, right? The flow dynamics, and given that the Froude number is more important here, we thought about using the shallow water equations as a way of predicting sediment transport and a way of solving the Exner equation for the bed evolution, right? So if you think about it, as I said, the shallow water equations we're going to consider for the flow, we are using a two-dimensional model, which means that we have as variables the water depth and the two components of velocity in x and y. These are vertically average velocities, right? Then we have to find in these two horizontal directions the components of bedload transport, and then compute the bed elevation in time. All the system coupled together, right? For the shallow water equations, here you have conservation of mass and conservation of momentum. It's connected to the bed elevation by the local slope, right? And to solve these equations is not simple, right? These are hyperbolic equations of wave propagation. We have had some experience on solving this with using shock capturing schemes that can actually resolve hydraulic jumps. The problem is that these numerical models are are computationally expensive in terms of the shallow water equations, and they take more time, and sometimes they require a smaller time step. The good thing is that we try, and the results that I'm going to show you so far, we've used our recent high resolution models, but we also try some simple numerical approaches to solve the shallow water Saint-Venant equations. For instance, if you implement the simplest monotone scheme that will converge for these equations, which is Lax-Fredericks, it works too, right? Even though this numerical scheme is very dissipative, in this case, as long as you don't have hydraulic jumps, it works pretty much well, right? And then the numerical solution of these equations will give us the magnitude of the vertically average velocity, right? So what we get from the solution of the model is the velocity magnitude, which is average on the water depth. But we need to be able to predict sediment transport. We need the bed shear stress. So what we did now was to compute instantaneously from the instantaneous mean velocity. We adjusted a logarithmic profile, okay? And with that, we can estimate, or we can have a value integrating this profile. We can have a value of of the bed shear stress at each point on the bed at each time step, right? And the idea is to use that value to predict the local transport. So in this case, we use England and Hansen's bedload transport equation, which is based on the definition of this bed aerial concentration times the sediment velocity or the particle velocity, used in this vectorial form as Kovacs and Parker's paper. So we have here the definition of the bedload transport formula, and this PEF is the probability or the error to be used in the aerial concentration is basically the number of particles that participate on transport. Is the probability, the percentage of particles in motion, basically. An important thing here is that this this critical shields parameter is calculated also at each point on the bed, because it also depends on the local bed slope, right? We have to consider, we have to calculate a lot of local inclination of the bed and the normal and tangent vectors to be able to compute what's the value of the local critical shields parameter. And to compute the velocity, we solve also for the instantaneous flow velocity. We solve a velocity of a sediment particle that considers drag, gravity, and the resistance, a resistant force, right? So we integrate for the bedload transport this dynamic equation to compute the local sediment velocity and then have a vector of bedload transport. That's the idea. And finally, to solve the Exner equation, this is probably the most difficult part because this equation is complicated. It depends mostly on the forcing, not on the elevation. So we tried to go as easy as we could. We implemented a predictor corrector, a McCormick scheme, that when you have wave propagation is unstable. So the way of making it, I'm really sorry about showing these equations. This is just to show you how we implemented this, but it's very brief, and I can answer some questions if you want some more details. But what we did is to implement this McCormick scheme, and we added a numerical dissipation to make it stable, which is Jameson's artificial dissipation, which depends on the local gradient of elevation, and we use a very tiny value of epsilon here. Just to scale the local dissipation. Okay? I'm sorry about the notation is because we use generalized curvilinear coordinates for the entire formulation. So as a summary, for the numerical models, we have either a Lax-Friedrichs or a very complicated TVD scheme with muscle extrapolation for the shallow water equations. With those references that I told you, for the bedload transport, we implemented a bedload transport vector from England's and Hansen's, and the Exner equation is solved with a McCormick scheme with Jameson artificial dissipation, and everything is discretized in a numerical grid in generalized coordinates. So we take the data that was recently published by Pascal and Bojorquez in 2021. They carried out, they showed 4 experiments. I'm going to show you here, as I told you, we are just working on this. We simulated first the case E3. This is the mean velocity water depth and the constant flux that is fed to the flume. Is a 2.5 meter flume with 0.04 meters wide, a slope of 3 degrees, and it was well sorted sediment with D50 equals 2.9 millimeters. So all the results that are reported are for this from the middle of the flume, 0.75 meters downstream, and the fruit number here is 1.44. So what we did is that we reproduced this numerically. We discretized the channel in 1200 times 30 elements, and we use a small time step of 10 to the minus 4. We are solving all the equations at the same time step and impose the same boundary conditions as the experiment on the upstream end. And actually, the results are really amazing. If you look at what we got from the numerical simulation, you can see how the antidunes are propagating upstream, as the flow direction and the bedload transport propagate from left to right in this case. So when we saw that we were able to capture the dynamics of bedforms in these conditions, we started to compare some of the results. And I see here, this is a line across the center of the channel for this 0.75 meters. And these are 250 seconds. And I plotted the same from the simulations. And it looks very similar, but I have a little bit faster bedforms that I will discuss about that with you. We have so much resolution that we can go deep inside this time stacks and look into. I changed the colors here because it looks like fire or hell or both. We can see in detail the contours of bed elevations at the center of the channel in time, and you see here there are some bedforms that really travel faster than others. So the way to analyze this quantitatively is really to compute the spectrum in space-time. And so we follow here the work that Michele Walla had done on dunes. We computed the Fourier transform and the spectrum on wave number and frequency of the data that you just saw. Here, lambda is the wavelength of the bedforms. And this is the amazing thing, that we only impose here the boundary conditions at the upstream, and you see the spectrum here. We have all this area here, not only the wavelength on the same range, but also the space-time distribution up to 10 seconds. The other thing is that we have other peaks at smaller periods and for the whole range of wavelength that do not appear on the experiments, right? We have this additional peaks that appear in the simulation. And the same thing happened if from this spectrum, if we compute the celerity of the bedforms, we reproduce the celerities at 0.01, 0.02, but also we have some other bedforms traveling faster in the simulation at higher resolutions in this case. So we're looking into that, and one of the things that we started doing is we tried, for instance, to compute the autocorrelation function of the bed elevation. You see that has this periodic component, but what is weird in our simulations is that the decay is very slow, so it has a very long memory. Which is something that totally different to what we had, or at least I had observed in the ripple simulations with turbulence. There seems to be, at least on the simulations, an overall structure that is larger than the size of just one bedform. The other thing that we computed was we performed this fluctuation analysis that you probably had seen before. You compute what is basically the standard deviation of the bed elevation at different scales. You sample the bed at different scales L, and you see that you can easily demonstrate that the moment where at the scale at which you lose correlation, at which you lose dependence, this diagram saturates and becomes totally flat because the standard deviation scales as 1 over the square root of L. So you see here that this saturates at about 0.3, and I also calculated other statistics, the average mutual information and things like that, and they also gave me that scale. If this is the same plot but in log scale, and you see that about 0.3, it turns flat. So we're investigating that and seeing how we can understand better the dynamics and see if we can really, because we see exactly what's seen in the experiments, but we also have some other conditions that are difficult to understand. So this model basically combines the 3 necessary aspects to capture the nonlinear interactions of the flow. So we implemented this model that makes the flow, the sediment transport, and the bed to interact. we modified the bedload transport to consider the instantaneous sediment velocity and the instantaneous aerial concentration. Even though this formula was developed for different conditions, we found a way to change it. And to be able to make the external equation to converge, we added a little bit of this artificial numerical dissipation that was enough to see the development of the bedforms. And we can reproduce quantitatively that, in fact, the dynamics that it's observed in experiments, but these statistics also show additional scale that of course require more analysis. And an important point that I think it's pretty amazing and I like about our model is that we don't require the implementation of any perturbation. The bed starts flat and the antidunes evolve naturally from the nonlinear interactions between the flow and the bed. The bedforms are naturally excited by the flow field. So we still have a lot of work to do, at least even if we try this case. And the idea is, as I showed you at the beginning, try to address the more larger scale and complex problems related to antidunes. First, we're going to look into all the characteristic geometry and try to develop expressions for bedload flux in case with antidunes. As I said before, for instance, even Michele's group has looked into new expressions to determine bedload transport, because if the bedforms do not deform that much, you can decompose the bedload transport due to the bedform and all the a fraction of bedload transport that doesn't that is passive, doesn't contribute to the evolution of the bedform at every position. But in this case, which is crazy, is that the bedform goes in one direction and the bedload transport goes in a different direction. So how we can use this model to improve our predictive capacity for bedload transport in the presence of antidunes. Then the idea is to explore the importance of other factors. What if we consider different sediment size attribution? What if we have wave breaking, hydraulic jumps? Is it important to have turbulence effects and things like that? Also here, and this is something that I probably should have discussed in more detail, but the streamwise grid size, the size of the discretization in the forward direction, is a little bit larger than the mean sediment size. So what I'm thinking, and this is one of the questions about seeing this fast bedforms propagating compared to the experiment. What is the role that really the artificial dissipation plays? If we increase the grid size, if the grid size keeps getting larger, we're going to need some sort of subgrid scale model for the morphodynamics. Is this artificial dissipation interfering with that? That's something that I'm not clear, and I would like to look into more detail. And at the end, I wanted to finish with this and this is something that the whole discussion is in this book chapter for gravel bed rivers that we wrote with Chris and Vaughn. The idea is that we can use this model to learn about more about nature, right? The idea that models are research tool to understand nature, and it's important to identify the set of processes and hopefully the minimal set of processes that are needed to produce a given phenomenon, like in this case. And this, of course, needs to be accompanied with good measurements in experiments or field observations to be able to accomplish that objective. So that's it. These are our emails. If you have questions or comments later, if you want to contact us, and I thank Megan and the funding from Sigida and a Fundacid project that we also have. Thank you.
Amazing. Thank you, Cristián. That was, I have so much to absorb right now. That was great. So the chat is now open for questions. So yeah, we can go ahead and fire away. In the meantime, I had one about the graph that you showed on your towards the end. I was wondering, what is the significance there for sediment transport? You're talking about where it kind of plateaued.
Yeah, sure. Let me go back. Yeah, this. I don't see a direct relationship for sediment transport. This is just a statistical analysis of the bed elevation fluctuations, right? So what basically tells you is that if you sample the bed at different scales, there will be a scale at which you're going to lose the spatial dependence. So the point is, and this is what we've been thinking about with Megan. If you go back here, you see that the wavelengths of the bedforms are 0.1 in that order. But according to this plot, and this is linear dependence, but it tells you that there's a 0.3 at which at 0.3 meters you lose correlation. I don't know if physically maybe that means that some of these bedforms travel in trains of more than one. There is a spatial dependence that goes beyond one antidune.
Okay. And I guess my question is always the possibility of integrating more than one grain size into your simulations, but that's too complex.
Yeah. Well, there are. If you've seen, there are studies in which you can do a model similar to this one, in which you can consider sediment size distributions, and you have to try to use a bedload transport formula that can deal with that. Of course, I don't know, Wilcock and Crow or something like that, and most of these models also need to deal with the changes on the sediment size distribution and the active layer. You rapidly increase the complexity, and that's very much more difficult. Yeah, I like also, and we've been working with some students and in the group on Lagrangian models, even simple grain models. Maybe that can also be used with this larger scale models to combine and get some insights at small scales that you can later upscale to larger scales. That's the idea. Pretty much.
Cool. Cool. So I think Megan had a question. I don't know if she's taken her hand down, but I can unmute you.
Well, first off, I was gonna the chat is not able. I'm still getting the chat disabled and not allowed to unmute. That's my first comment, and I'm happy to defer my question because I'm involved in this. But I was wondering if Cristián, you could comment when we see these the anti-dune video, and I think that it's sort of mesmerizing to watch them. You see the kind of anti-dunes; they sort of seem like they walk across the channel, and so I was wondering if you could comment on the effects of the channel walls on what you expect the bedform behavior.
Yeah, good point. No, in this case, that's an excellent question, and I don't know if we actually can see some effects on the walls. The bedforms are, and I'll see if I can go back and show you that. Yeah, here in the simulation results. Yeah, I don't know if they probably have some effect, the sidewalls, but these bedforms are more or less two-dimensional. The deviation is very, very tiny in this case. That's something to investigate. And as I said, this is something that came from the model without doing anything, right? This tiny differences in the cross stream direction, we're able to generate the evolution of the bedforms like that. They're walking somewhat. Yeah, that's a good observation, but I don't have an answer yet. All right. Yeah. There is a question on the chat, Rebecca. I don't know if you want me to.
Yeah, we
read it
also
out.
had there was someone else with their hand up.
Okay.
One second.
You're the boss. You're.
Okay, I will ask Mehred.
Yes,
Is that right? Yeah.
Mehred, yeah. Thank you for your presentation first. And my question is that, do you have a two-dimensional case study to be able to observe alternate bars, or you focused on one-dimensional simulation?
Yeah, well, this model is in fact two-dimensional. The animation you just saw is two-dimensional. Actually, that's also an excellent question. When I started playing with this, the model, like, it has a life of its own. I just, as I told you, just give it the upstream boundary conditions, and it develops like a channel, right? When I started playing with the model, in some situations, but I didn't investigate much more than that. I saw some development of alternate bars, in fact, but I didn't. I just saw it and said, "Oh, that's cool. Maybe this model can do it." But I didn't. I wanted to get into these specific experiments, and I didn't look in more detail into that. But yeah, maybe we can find a good experiment or good observation and see if the model can deal with alternate bars too. Mm-hmm.
Cristián, so we have some questions in the chat. I will start with one question by Anne Bernard. Dear Cristián, thank you a lot for this very interesting talk. Now it is commonly said that antidunes are rarely preserved in the sedimentary record. What can we learn from your model about internal structures of these bed forms and their preservation potential in the sedimentary record?
Yeah, that's also that it's something that I should have wrote in the future perspectives of this work. I think that's something that we can also do. There are models that on top of my mind, Kate Leary probably with Bamsi Ganti tried to develop these models to build the sedimentary records from the bedforms that are going on top, and you can try to make these two models talk in a way. I think that's another question that is open, and as I told you, this is my first presentation on this topic, and I think that those are things that might have some. It might be interesting to explore. It's a lot of fun.
So I think Chris Unsworth, sorry, has a question. So you can unmute yourself, Chris, if you want to ask directly.
Thank you. That's a really cool presentation and a great model. It's good to see. I had a couple of things. One was like when you're talking about the antidunes developing, that's really cool. I put a link in the chat now to a paper I'm not involved with, where they do some lab experiments where they look at antidunes on bars. And that you might be able to get some data from them to try and validate your model with that. So
yeah, thanks
that was a really cool piece of work. So that's a suggestion of something to do. But I was really interested that you didn't need to add noise to your bed to initiate the bed forms. Usually with these sorts of models, you do need to add something to it. I was wondering, like, and I'll get you to discuss why you think that is, but also, do you think it would happen if the flow was subcritical?
Yeah, good question. I think that the easy answer it's for the second question. I think it wouldn't happen because the supercritical flows, especially when you have ripples or dunes, I think that for their initial development, you need turbulence in one way or another, and that was my experience with with three-dimensional simulations of ripples developing around obstacles and stuff like that. We needed, it's in those cases, it's the forcing. You need to solve turbulence in those conditions to produce, and that's what also Ali and Fotis saw. The bed fills out with this crosshatch patterns, which are mostly due to turbulence. If you don't solve turbulence, you're not going to have any development, initial development in those cases. Probably later, some issues like flow separation and stuff like that might be important. So yeah, that's the answer to the second question. Why do I think this developed naturally? I think you still need perturbations, and maybe the numerical solution, the natural numerical solution, it gives enough perturbations to the flow to be able to develop that. There are tiny differences probably that triggered but I didn't have to worry about that. That's the crazy thing, that it's I don't really know. One of the things that I was thinking, but if you look into the theoretical analysis of antidunes, they're mostly based, for instance, Kennedy and people later, in either linear stability and try to understand where the modes that excite this, and try to see if we match those conditions, and if this system, which is non-linear, more complex, can be connected to those linear stability analysis. But again, I think it's the numerical solution that probably triggers naturally those perturbations.
It's the classic chicken and egg problem, isn't it?
Yeah.
Cool, good stuff.
Great. Okay, so we have a question in the chat from Hugh Sinclair. He says, I don't understand how they can migrate at such different velocities if they are mimicking the surface flow form. Are there standing waves migrating upstream and superimposing and interfering with each other?
Yes, I think that's the answer. You have, when you see the solution, the free surface follows closely the antidunes, and I think that this tiny variabilities that start to erode the lee side push the antidune backwards and updates again the flow. That's exactly what happens. They're moving slowly. So yeah. No, thank you, Hugh. Great question.
All right, so Philippe, do you want to take the next one?
Yes, but I think we have someone in the chat that want to, sorry, in the participants that want to raise a question directly.
Yeah, Ivan. Okay.
Ivan.
To unmute. Go ahead, Ivan.
Yeah.
Great experiments. Yeah, great experiments, Ivan. Thank you.
Yeah, thank you very much. I was really amazed to look at your presentation. It was really interesting and inspiring too to continue with this work. And I was trying to, I don't know, to raise a point for an interesting discussion in which related to the point in which you discussed about the time let's say correlation that seems longer than what we expect. And that related to the trains and to the to the question that you just answered. Because I think that then I can see the antidunes during the experiments that I do, and when the antidunes have these merging processes sometimes. That now probably we will need more time to look at your profiles, and probably that is missing. I don't know in the plot that in the video that you showed, but we need time to look at it more in detail. But it's interesting to see that when we have these merging events, the acceleration of the antidune comes also from this deformation that acts at the internally in the trains, and I think that this could be an interpretation of that. And probably this is also a signature of the fact that even if it doesn't seem in the video, you have this kind of merging events inside your model. So it was really amazing to see that. Thanks.
Yeah, and that's it. No, thank you. And I really this is what makes me really excited about what we all do, right? The ability that we can look at a difficult problem in nature from different perspectives, from the experimental, from the numerical, on the field, and get these insights. I find it amazing, really. And thank you, Ivan, for your comments. Yeah, I didn't comment that either, but I saw this merging events that some of the bedforms started moving faster and then catch up with the other one. And again, I haven't looked into those details and when they occur and why and what are the consequences. Excellent point.
Okay, so we have another question in the chat by Merdad Kani. And how the bedload transport will change versus time? Is it a constant value?
No. The only constant is the input. I input the constant bedload transport at the upstream end of the channel. No, it's mostly if I look at it, if I stay in a point, it's clearly periodic, and I see that there's a large variability, and that's another point because Ivan in his experiment, he plotted the distribution of bedload transport, and we're going to look into that too. But I didn't record it originally, but now we're gonna do a more complete analysis of that thing.
Okay, and I think we just missed one question in the chat, so I'll go back and then we'll go to Ivan. Mirdad said, I have another question, is how, what does the distribution of the number of active particles look like?
Yeah, it looks like the bedload transport, basically. This model, if you remember, had the active particles times the velocity. So when the local shields parameter is lower than the critical, it's zero. Everything. The aerial concentration and the bedload transport are zero. If not, it's the aerial concentration is just a factor on top of the velocity, so they look very similar both. Yep.
If I may raise a question, Cristián, a big advantage of having a numerical model is that you can very easily change the parameters of the model. Have you tried changing the length of your channels, the height of the flow, or other conditions?
Yeah, not yet, but that's another good point, especially if any of you have experience or are interested in numerical models or use models in one way or another. This model, for instance, has many parameters, not only related to the geometry, but also a lot of other things. The drag coefficient of a particle, the friction coefficient of a particle, those things have been computed. All this formula from the Englund and Hansen are just curve fitting from many experiments that they collected in. So we not only have some values that are specific to this particular experiment, but I just use values that have been verified in the literature, probably in other conditions, and that happens with most of the models. You have a lot of variables that you have to use, and in some cases you're pretty sure they're going to work. In other cases, it's important sometimes to explore what are the consequences of changing that or not. as I was saying before, when they asked me the previous question, when I implemented the model before trying events experiments, I started playing with the model, I started with some different conditions, you know, thinking Megan was having ideas on this bar-built estuaries, and I made some simulations, and even one of those I started seeing like alternate bars and things like that. But it's difficult to tell, especially within each model, how sensitive they are and what are the consequences of changing one or another parameter.
Okay, thank you very much.
Mm-hmm. Ivan had the hand. I don't know if it's an old hand or a new hand.
Thanks. No, it was a new one related to the bedload transport, because we tried to propose in our work the framework, a dimensionless relationship for the bedload transport. And it would be for sure interesting to compare also with the observation that you can do in a numerical model, because we tried to work on that relationship, but finally we were able to propose it because we had the luck to see the spectra that were giving us the suggestions for the interpretation. But finally, it would be really interesting to compare that, and especially the fact that the longest wavelengths tends to reach a plateau in the velocity, given probably also to the effect of the inertia. And this in a numerical model, it's much more easy to test, and it will be really interesting. And just in case you regarding to the length of the flume, we already run some experiment with a 6 meter long flume. So now I'm just analyzing, but they will come.
Excellent.
One
excellent.
day.
I'm very excited about that. Yeah. Thank you.
Thank you. Thank you very much.
Okay, great. So I think nobody else has their hands up. I think we've answered all the questions in the chat. So I guess thank you very much, Cristián. That was really great.
Thank you. Thank you all for inviting me. I hope it was, to me, it was very interesting. And no, thank you. Great. Thanks all for coming and staying.
We have lots of people clapping in the chat, so you can feel it virtually.
All right.
So that's it. Thank you, everyone. And hopefully we'll see you not next week, but the week after for our next talk. Thank you very much.
Bye. Thank you.